Hello friends, we met again in the electromagnetic induction. In this chapter, we will learn about magnetic flux, electric motive force, Lenz's law, self-inductance, and energy of inductor. Now we see number 1. The conductor shown in figure below has an area of 0.2 meters square. A constant magnetic field B is 0.15 Tesla, pointing in the x positive direction, fills the space independent of the loop. Find the flux through the conductor in each orientation shown. We know that the formula of flux is BA cosine theta. With theta is angle between the magnetic field line and the normal line of surface. So if we see number 1, we will see the magnetic field is perpendicular with the surface. So that we first draw the normal line. Normal line is a line which perpendicular with the surface. Normal line. We see normal line and magnetic field line B is parallel, so that the angle is 0. So we calculate the flux for picture number 1. Flux is BA cosine theta. B magnetic field is 0.15. The area A is 0.2 cosine 0. So that we get the value of flux is 0.03 Weber. Okay. Next we see the picture number 2. In picture number 2, the normal line we draw perpendicular to surface is this line, so that if we see the theta, the angle between B and N is this place, so that the angle theta is 90 degree minus 60 degree, we get the 30 degree for the angle theta. So we calculate the flux in this picture number 2. Flux is BA cosine theta B is 0.15, A is 0.2 cosine 30. We get the 0.03 times 1/2 square of 3, so that we get the 0.03 0.015 square of 3 Weber. Okay, this is explanation of calculating the flux in surface. Okay, next number 2. A coil having 20 turns of wire is removed in 5 milliseconds from between the poles of a magnet, where its area intercepts a flux change of 3 times 10 to minus 3 power Weber. Determine the average electromotive force induced in the coil. We know that the formula of EMF E can be found with the formula of N times change of flux divided change of time. Yeah. So that we state that the known quantity is time, turns, and the flux change. Okay, we input this value. Turns n is 20. Change of flux is 3 times 10 to minus 3 power divided by 5 milliseconds. 5 times millisecond have to be changed into second. So times 10 to minus 3 power. So that we get the result 20 divided by 5, we got 4. Times 3, we get 12 volt. Okay, this is explanation to searching for average electromotive force. Next, number 3. A coil consists of 50 turns, is in area of magnetic field which parallel direction with the coil area. The magnitude of magnetic field change against the time according to equation B equal to 10 to minus 3 power sine 100t. If the area of coil is 200 centimeters square and the resistor in coil is 4 ohm, find A, the equation of magnetic flux as a time function, B, the maximum electromotive force, C, the value of maximum current. Okay, we answer A. Yeah. The equation of magnetic flux as time function. From before, we know that the formula of flux is B A cosine theta. Okay, so we input the B, 10 to minus 3 power sine 100t times A area is 0.02 meter square cosine 0 degree because the angle is 0. We got the value 2 times 10 to minus 5 power minus 5 power sine 100t. Okay, we got the flux function as time function. Next, B. What is the maximum electromotive force? The electromotive force EMF can be found with the formula N d flux dt, with d flux dt is derivative from flux function. Okay, so that we input the value of turns 50 times d flux dt d flux dt is 100t, 100 we took outside, and the sign changed into cosine, and this 2 times 10 to minus 5 power. Okay, we got the derivative from flux function, so that we this 50 times 2 times 10 to minus 3 power cosine 100t, so that we got the 0.1 cosine 100t. Okay, we have to remember that the cosine equation will got the maximum value if the value of cosine is 1. So that the EMF maximum is 0.1 volt. Okay, next we find the value of maximum current. The current can be found with the formula EMF divided by R. If the value of current maximum, then the EMF got to be maximum too, so that this maximum current will be 0.1 from option B, divided by 4, and then we got the value of maximum current is 0.025 ampere. Okay, next number 4. Metal stick PQ makes contact with 2 parallel wires and completes the circuit. The stick has length 15 cm. The circuit is perpendicular to a magnetic field with B 0.5 Tesla. If the resistance is 20 ohm, how large a force is needed to move the stick to the right with a constant speed of 8 meters per second? Okay, where is the direction of current in stick PQ? The equation is force and the direction of current. Okay, the force is the Lorentz force. The Lorentz force in the circuit is B times I times L. Magnet induction times current times length. Okay. Only currents is not in the problem. So first we have to find the value of current. Okay. The value of current in electromagnetic induction can be found with the equation current is electromotive force divided by R. Okay, so first we find the EMF E is B R V. Okay, the B is 0.5 Tesla times L is the length of conductor PQ is 15 centimeter changed into meter times V, the speed is 8 meter per second. Okay, we find that so this value is 0.6 volt. Then we find the current I. 0.6 divided by 20. We got 0.03 ampere. Then we find the Lorentz force F, B times I times L. We got the value B 0.5 times I 0.03 times L is 0.15. So that we got the value of force is 0.00225 Newton. Okay, we got the force already. Then we find the direction of current is stick PQ. So according to right hand rule, we got the thumb finger show the direction of velocity, index finger show the direction of magnetic induction, and another 3 fingers show the induced current. So that if we see this direction of velocity is to the right side, so we got our thumb finger to the right side. Then the magnetic field is got the symbol cross, so it means the magnetic field have to be into the paper, so that we got our index finger into the paper, so that we will got the another 3 fingers direction to upside. It means we get the direction of induced current to upside. Okay. Next, problem number 5. A magnet below will be moved into the circle conductor. What is the direction of induced current in conductor? Okay, we see this magnet will be moved, become closer to the wire. Okay, first we have to draw the main flux in the magnet. The main flux in the magnet have direction to the North Pole. This is first step. You have to do this step first. This we write the symbol is main flux or initial flux. Okay, then we look the direction of magnet become more closer or become farther, so that we get the direction the magnet is become closer, become near to the wire. According to the Lenz's law, if the magnet become closer to the wire, then the wire will have more increase the induced flux in itself, so that the induced flux will have opposite direction with main flux. Because magnet move closer to wire, so that the main flux or initial flux is the direction to the right, so that the induced flux in wire will have opposite direction to the left. This is step number 3. So that using right hand rule, that if our right hand fits the thumb show the direction of flux, then our fist will show the direction of current, so that we get this direction of current to upside. This is step 4, and final step, we got the direction of induced current. Okay, we repeat. Step number 1, we have to state the direction of magnetic flux is to the north. Step number 2, we see the direction of velocity magnet is become closer or become farther. Okay, velocity is become closer to wire, so that in step number 3, because magnet move closer to wire, then direction of induced flux will behave opposite direction with main flux, and we have the opposite direction is to the left. In the step number 4, using the right hand rule, our thumb finger show the direction of flux, then our fist, another 4 fingers, show the direction of current, so that we get the direction of induced current to upside. Number 6. A coil has an inductance of 0.3 millihenry, and the current in it changes from 2 ampere to 0 in a time of 5 milliseconds. Find the magnitude of the average induced EMF in the coil during this time. Okay. In inductor, we can calculate the EMF E using formula L times change of current divided by change of time, so that we look the value of inductance from problem is 0.3 millihenry. We have changed to Henry times 10 to minus 3 power times, it changed from 2 to 0, so that the change is 0 minus 2 divided by time 5 millisecond, 5 times change into second, 10 times to minus 3 power, so that we get the value (0.3 times minus 2 divided by 5). We get the value, this is minus 0.12 volt. Okay. Next, number 7. Calculate the self-inductance of a 1200 turn solenoid in which a current of 9 ampere produces a flux of 1.5 times 10 to minus 4 power Weber in each turn. Okay, the self-inductance have symbol N, turn. Turn is symbol N. Current has symbol I. Flux is symbol flux. With this symbol in the problem, we can write the formula of self-inductance is L equal to N times flux per I current, so that we can calculate this value. The amount of turn is 1200 times flux 1.5 times 10 to minus 4 power divided by I 9 ampere. So that we get this value by 6 and this 200, so that we get the value is 0.02 Henry. Okay, next, number 8. A solenoid with 150 turns in 80 cm long and has a radius 2 cm. How much energy is stored in its magnetic field when it carries a current of 40 ampere? Okay, when we have to find the energy in solenoid or in inductor, we have to use the formula. Energy is 1/2 times self-inductance times current square. In this formula, we have found the value of self-inductance yet, the L. So we first find the value of self-inductance L. The formula of L is permeability times N square times A divided by length. So we got the value is 4p times 10 to minus 7 power times 150 square times A. Solenoid has circular surface, then the area is PR square. We have changed the radius into meter divided by L, 0.8 meter. So that if we reach calculator, we will find the 450,000 times 10 to minus 11 power times p square. So that we get the number is 45 times 10 to minus 7 power times p square. Okay, this value we input to formula energy, so that energy is 1/2 times 45 times 10 to minus 7 power p square times 40 square. The current is 40, so that we get the value 36,000 p square times 10 to minus 7 power because the p square is closer to 10, so that we can get the value. This become 36,000 times 10 times 10 to minus 7 power. Then we have the final value is 0.036 joule. Okay. Number 9. The coil in an AC generator consists of some turns of wire. Each of area A is 0.02 meters square. The coil rotates in a 0.06 Tesla magnetic field at a constant frequency of 60 Hz. Find the amount of turns in wire to produce maximum induced electromotive force 170 volt in the coil. Okay. This generator have formula to find electromotive force is EMF equal to B magnetic field times A area times angular velocity omega times N amount of turns. Okay, we input the value of electromotive force is 170 volt equal to B is 0.06 Tesla times A area is 0.02 meters square. Angular velocity can be found with the formula 2 times P times frequency 60 2pf. Okay, times the amount of turns is, we have to find it. Okay, we calculate this. 170 equal to 0.06 times 0.02 times 120 times P times N. Okay, so that if we calculate this 170 equal to 0.06 times 0.02 times 120, we get the 0.144 P 3.14 times N, and we get the value of this is 170 equal to 0.45 216 times N. And if we find this value, we will get 170 divided by 0.45 216. We will get the closer value to 376 turns. Okay, this is solved problem about the electromagnetic induction. Wish you more understand in this problem and get the high score in the examination. Goodbye, see you again in the next lesson. Thank you for watching my video.